Good day, everyone. My name is Paul Angelesi. You can also call me Paul. And today I'll be going to discuss my thesis about optimizing audio performance through speaker equalization calibration heuristics in controlled acoustic environments. Let me start by introducing the core of the study. When we listen to sound in a room, the experience is heavily influenced by room acoustics. Factors like reflections, absorptions, and standing waves can distort what we hear, causing issues like exaggerated bass or loss of clarity. To address these problems, speaker calibration is commonly used. It's a process that optimizes the speaker's output to correct for these acoustic issues. Traditionally, this is done manually using equalizers or what we call EQ, tone sweeps, and precise measurement tools like real-time analyzers and calibrated microphones. However, manual calibration can be time-consuming and subjective, often requiring expert knowledge. This study aims to compare different calibration heuristics, including both traditional algorithmic methods and modern AI-based approaches. It uses a calibrated microphone to accurately measure the room's acoustic response and apply each heuristic to see how well it corrects the sound. This study is significant for several reasons. First, it investigates whether AI can enhance speaker calibration beyond what current automated software can achieve. Most existing tools are limited by fixed algorithms, but AI offers the potential to adapt and optimize more effectively. Second, by making the calibration process easier and more accurate, this research could help make high-quality sound more accessible to everyday users, not just audio professionals. It reduces the need for expert-level knowledge and complex manual adjustments. Third, the results of the study could influence the future of both consumer and professional audio calibration tools. AI-driven solutions may soon become the standard for home, studio, and commercial applications. Finally, this research broadens our understanding of heuristic-based calibration methods, showing how traditional and modern approaches compare and where improvements can still be made. This study focuses on comparing AI-based and algorithmic speaker calibration methods. Specifically, it evaluates how accurately each method can correct the speaker's frequency response. This study uses a 10-band parametric EQ for all calibrations to maintain consistency, and the AI approach in this study is powered by the GPT-4o model. However, there are some important limitations to note. The results of the study may not directly apply to different room types, larger spaces, or environments where acoustic conditions change frequently. It also does not cover multi-room setups, spatial audio systems, or multi-channel surround sound configurations. Finally, to maintain objectivity, the study is limited to tone sweep measurements and does not include human listening tests in order to eliminate listener bias. In manual calibration methods, room acoustics can be significantly improved through the use of absorbers and diffusers, as highlighted in the study by Arvidsson and colleagues. Their research showed that absorbent ceilings are particularly effective in reducing overall energy levels and lowering reverberation time, which helps control unwanted echoes in the room. Absorbers not only reduce reverberation, but they also enhance speech clarity, measured by the C50 metric, making sound more distinct and easier to understand. Diffusers, on the other hand, help balance sound clarity and reverberation without significantly changing the overall sound strength, known as G. This literature emphasizes that acoustic treatments like these are essential in fine-tuning room acoustics as part of the manual calibration process. Moving on to comparative studies, research has explored the use of heuristic methods such as rule-based algorithms and optimization techniques for speaker calibration, as discussed by Primavera and Secchi. These studies offer structured, repeatable approaches to calibration. Floyd Tools' work discusses the limitations of digital signal processing, or DSP. While DSP can correct some frequency response issues, it cannot fully address problems caused by reflections, reverberations, or differences in sound from one seating position to another. This highlights the complexity of room acoustics and the limits of traditional solutions. Additionally, MathWorks conducted studies showing that automated filter design for room equalization can result in smoother frequency response and more natural sound, often outperforming manual calibration in terms of consistency and efficiency. For the methodology, all tests were conducted in a controlled, acoustically treated room. The room was equipped with sound-absorbing panels, bass traps, and diffusers to minimize external noise, reflections, and other acoustic interferences. This controlled environment ensures that any changes observed are purely due to the calibration heuristics being tested. This study evaluates 3 different speaker positioning setups. First, the standard positioning, where speakers were placed 1 meter away from the front wall, forming an equilateral triangle with the listening position, which was 4.25 meters away. This follows recommended best practices for achieving balanced stereo imaging according to KEF, a reputable speaker manufacturer from the United Kingdom. Second, the speakers were placed closer to the wall to observe how boundary reinforcement can increase bass energy and potentially introduce frequency imbalances. Third, we placed the speakers farther from the wall to study how increasing the distance reduces reflections and alters the frequency response. For the measurement process, a 256K length tone sweep is used ranging from 20 Hz to 20 kHz with a 48 kHz sampling rate to capture detailed frequency response data across the audible spectrum. So for context, this is what a tone sweep sounds like. It starts off with the low frequencies and slowly and gradually moves up to the higher frequencies. The equipment chain consisted of a Windows machine as the audio source, connected to an external digital to audio converter or a DAC, then to an amplifier using balanced XLR connections. The speakers were connected using a 7-gauge oxygen-free copper cable with bi-wiring applied if the speaker supported it. For accurate measurements, a mini DSP UMIC 1 calibration microphone is used with its specific calibration file loaded into the system to ensure precise response readings. All baseline and post-calibration measurements were captured using Room EQ Wizard, a reliable software tool for acoustic analysis. The EQ adjustments were applied through a 10-band parametric equalizer implemented via software on the Windows machine, ensuring consistency throughout the study. This study uses a flat target frequency response because it's the most neutral and widely accepted baseline in audio calibration. A flat response means that all frequencies are reproduced at the same level without boosting or cutting any specific range. This allows us to focus on correcting room acoustics subjectively without introducing personal sound preferences, making it the best reference point for comparing different calibration methods. The first calibration method is the highest to lowest deviation approach. In this method, the distance from the target decibel level is calculated by taking the absolute value of the difference between the measured frequency response and the target dB level at each frequency. Once the distances are calculated, the frequencies are arranged from highest to lowest, based on how far they deviate from the target. From this sorted list, the top 10 frequencies with the largest deviations are selected. These are the points that are prioritized for correction using the 10-band parametric equalizer. The second calibration method is the k-means clustering. In this approach, k-means clustering is applied to the frequency response curve, dividing it into 10 clusters. This groups frequencies that share similar behavior or characteristics. sklearn's k-means algorithm is used to perform the clustering. Once the clusters are formed, the centroid of each cluster is identified, which represents the average or most central point within that group. These 10 centroids are then used as the target frequencies for adjustments in the parametric EQ. The third calibration method is logarithmic distribution or linear distribution. In this method, 10 frequencies are evenly distributed on a logarithmic scale from 20 Hz to 20 kHz, since audio works logarithmically instead of linear. NumPy's log space function is used to calculate these frequencies, ensuring that they are properly spaced according to the way humans naturally perceive sound, since our hearing is more sensitive to changes on a logarithmic rather than a linear scale. These logarithmically spaced frequencies are then used as the target points for adjustments in the parametric EQ. The fourth calibration method is AI-based calibration. For this method, the measured frequency response is exported as a text file formatted in pairs of frequency and their corresponding decibel levels. This provides the AI with a detailed snapshot of the room's acoustic profile. The AI model, powered by GPT-4o, is provided with a structured prompt that includes specific details about the room setup, such as room dimensions, the distance of the speakers from the wall, the distance between the two speakers, and the distance from the listening position to each speaker. For data analysis and evaluation, Manhattan distance is used to measure the difference between the target frequency response and the post-calibration response. A lower distance indicates that the calibration was more successful in bringing the frequency response closer to the target. Additionally, we categorize the speakers into 3 groups based on their initial distance from the target response: close, moderate, or far. This is an example of one of the results. The red line is the uncalibrated measurement. The dark green line should be the target as to what it should be, and the other lines are the post-adjustment measurements. The stock configuration, which has no EQ, had the highest average Manhattan distance at 4,370.98. This shows that default settings often fail to match the target response, especially in challenging room conditions. All the calibration heuristics tested performed better than stock. The AI-based achieved the best results, cutting the Manhattan distance nearly in half to 2,201.01. The linear and highest to lowest heuristics also improved the response but were less effective, with average distances still above the 2,900 range. These methods are simple but lack flexibility. The k-means heuristics performed in between, offering better calibration than traditional methods but still not as adaptive as AI. To compare the performance of the different heuristics, we used the Friedman test, a statistical method for checking differences across multiple test conditions. The test result showed a very high statistic of 672.60 with an extremely low p-value. Thus, we can confidently say that the heuristic performed differently from each other. There's a significant difference in how well each method can correct room acoustics and optimize EQ settings. After confirming that the heuristics performed differently, we used the Nemenyi post hoc test to compare each method against the others. The results showed that AI heuristic consistently outperformed all other methods with highly significant p-values. The highest to lowest heuristic performed better than stock, but its difference with linear was not that significant. The k-means heuristic was better than stock and linear, but still did not match AI's performance, and the linear method was less effective overall, but performed similarly to highest to lowest in some cases. To conclude, the AI-based calibration consistently outperformed all other methods across all tests. It achieved an average Manhattan distance that was 50% lower than the uncalibrated stock configuration, showing its clear advantage in improving frequency response. Traditional methods like logarithmic and highest to lowest showed only limited effectiveness and lacked the adaptability needed for complex room acoustics. The k-means heuristics showed some potential but still could not match the precision and consistency of the AI approach. Finally, our statistical tests, the Friedman and Nemenyi analysis, confirmed that AI's superior performance is statistically significant. For professionals, it is recommended to adopt AI-driven speaker calibration in professional environments for more accurate and consistent results. It's also valuable to develop dynamic calibration methods that can run multiple tests while changing speaker positions to automatically find the optimal placement. For future research, future studies can explore hybrid models, combining traditional methods like k-means for initial calibration with AI for fine-tuning. It would be more useful to design systems for large-scale setups like multi-channel surround sound in cinemas or home theaters. Researchers can investigate if similar heuristics can apply to subwoofer calibration, particularly in setting low-pass filter cutoffs and EQs. Finally, exploring custom target frequency responses may help adapt calibrations to individual sound preferences. That would be all for me. Thank you for your time and for listening.